Okay, so in this video we're going to talk about alternating series and absolute convergence. Now, so far we've talked about kind of series that are positive. That's been one of our restrictions. But in this section we're going to talk about what to do when our series aren't entirely made up of positive values. So essentially, the previous tests only work with series that have positive terms. So we just can't use those things on non-positive series. So obviously not all series are positive, and many are what we call alternating series whose terms alternate in sign. So basically what that means is that an alternating series is a series whose terms are alternately positive and negative. So in this case, we have like positive, negative, and so on and so forth. Here we have negative, positive, negative, positive. These are both alternating series, and the way we show these and the way you recognize them is with this -1. And then we either take it to like n plus 1, n minus 1, or something like that to ensure that our first term here is positive. So in this case, n minus 1 means that your first term would be 1, minus 1 is 0. Anything to the 0 power is just 1. So that's a positive then. And then the second term would be negative because it'd be 2 minus 1. Now, like I said, this is one way to show it. We can also show it with like a positive. So if we had something like this, plus 1, that would also work. And technically speaking, there's infinitely many ways we could do this. We could say like plus 3 if we really wanted. That's kind of silly, but we could do that. And so generally you'll see -1 or +1 depending. If we want it to start with a negative, we would just have it to the end. So the thing to keep in mind is that basically this portion determines the alternating signs. This part is the part that's like the actual values. Okay, so this is what we will be referring to as b sub n in just a little bit. Okay, so if we have an alternating series, so we're going to use the alternating series test. So if we have some generic alternating series, now it doesn't really matter that this is like, in this case, an n minus 1. It's not restricted by that statement here. But what we need to pay attention to is we have some alternating aspect, and then we have b sub n, which is non-alternating, and it's positive only. So the alternating portion is going back and forth between positive and negative, but this b sub n portion is always positive. That's a requirement of the alternating series test. Then, if it can satisfy the condition of b sub n plus 1 is less than or equal to b sub n for all n, and this is also kind of not necessarily true, but what we're saying here is that as long as every subsequent term is smaller than the previous one, then this should be okay. But realistically speaking, we often use this of like all n, but realistically speaking, we mean all n beyond a certain point. So as long as we can show that it's decreasing after some point along our series, then that's actually good enough. But in general, we refer to it as all, and many of them will be for all. But you might have a series that initially goes up and then comes down. In which case, as long as it's going down after some point, in fact here or whatever, then that's good enough. So we just need to show that each term is smaller than the previous one, and then we also have to show that the limit as n approaches infinity of our b sub n goes to 0. If we can show this, then our series is convergent. If we can't show this, then it's not. All right, so let's see this in action. So first of all, we have what we call the alternating harmonic series. Now we know that the harmonic series is a p series, 1 over n. Okay, if we just had the harmonic series, 1 over n diverges because this is n to the 1, and any p series where the power is less than or equal to 1, it's going to diverge. So normally this would diverge, but with an alternating harmonic series, what we need to look at is going, okay, well, we're going to do the alternating series test. So the alternating series test tells us that first of all, we need to show that two things. We need to show that our b sub n plus 1 is less than or equal to b sub n for all n, and we need to show that our limit as n approaches infinity of b sub n is 0. So let's take a look at what b sub n is, first of all. Now, as mentioned, this portion here is just alternating. This tells us that the first term is going to be positive and the next term's negative, and so on and so forth. So the rest of it is our b sub n. So our b sub n then is this 1 over n. Again, just the harmonic series here. Okay. So what we want to see is, okay, first off, whether b sub n plus 1 is less than or equal b sub n. Now, there's a couple ways we can do that. First of all, we simply just compare the two values. So b sub n plus 1 is 1 over n plus 1. As a reminder, what these things really stand for is this is like saying b of n plus 1. We could use function notation to describe our sequences. We just usually don't, to make sure that it's very clear, like that we're dealing with sequences and that our domain is not all real numbers, it's the natural numbers. But we can describe them as functions if it helps you understand what we're doing. We're replacing n in our b sub n function here with n plus 1. So that's this thing. And that's less than or equal to our b sub n, or b of n, or 1 over n. And we want to know, is this a true statement? Now, if we take a look at this thing, it's pretty obvious, I think, that we can see these two things are the same on top, so we're just comparing their bottoms. The bottom here is bigger than this one, so anytime the fraction's bottom, okay, the denominator is larger, then it's a smaller number because we're breaking it up more times. So clearly, this is always going to be smaller than this one, so that's true. Now, another option is kind of a fallback if we need to show this thing. Another option is to think about, when is our sequence b sub n, or let's talk about in terms of b of n, when is this thing like decreasing? Now, if you think about a decreasing function has a negative slope. So essentially what we can do is treat this like it's a function, like b of x, maybe 1 over x. And we want to think, well, when is this decreasing? When does it have a negative slope? So we just take the derivative. b prime of x would be negative 1 over x squared. And we want to know, all right, what values of x would, in the point that we care about, because realistically speaking, we actually only care about the natural numbers, so that is 1 onwards, from 1 onwards. But what values will lead to this being negative? And if you think about it, no matter what x we choose here, it's always going to be positive, and a positive divided by a positive is a positive, and then we have this negative sign. So like all numbers will work. So we have a negative slope, for all values of n. And we care about n. We don't actually care about n, but n greater than or equal to 1, which is what we're dealing with, is fine. So that implies that it is in fact decreasing. But again, this is kind of my fallback, is if I can't definitively show, or in a very clear manner show, that these two numbers are in fact, this relationship is true, then what I do is I go to checking the derivative. All right, so we've checked that out. This works. b sub n plus 1 is in fact less than or equal to b sub n for all n. Okay, now what we want to do is we want to go to, what is the limit? So the limit as n approaches infinity of b sub n, that is 1 over n, is going to be 1 over infinity, which is 0. So that checks. So this is convergent. So we can show then that this alternating series converges, and in fact the alternating harmonic series does converge. So the alternating series doesn't, the harmonic series doesn't, but the alternating harmonic series does. Okay, so let's take a look at another one. So we're going to test this series for convergence or divergence. So we want to see, is this convergent or not? Again, the idea here is that if we can show something converges, then we can um, approximate the infinite sum or waste time trying to find the infinite sum. So it just depends on what we want. Do we want it exact or whatever? But you don't want to waste time trying to find a sum if it diverges, because it's not going to exist. So that's why it's important. And we'll get to approximations in just a second. So first of all, let's recognize what b sub n is on this thing. And also, if you think about this series here, our first term is going to be positive, okay? Because when n is 1, 1 plus 1 is 2, the squared of this is positive. So let's think about what our sequence actually looks like. It looks like 1 over square root 2, negative 1 over square root 3, 1 over square root 4, which I recognize to be 2, but I'm just making sure we can see this pattern, negative 1 over square root 5, and so on and so forth. Okay, so that's what this looks like. Now, our b sub n is, again, the part that isn't our alternating portion. So that is 1, oops, go away thing. It is 1 over the square root of n plus 1. Okay, so this is our b sub n. So again, what we need to show is that b sub n plus 1 is less than or equal to b sub n, and the limit as n approaches infinity of b sub n is 0. These are the two things we need to show to see if it's convergent. Okay, so let's start with b sub n plus 1. b sub n plus 1 is 1 over the square root of n plus 1, which is less than or equal to 1 over the square root of n plus 1. Hopefully, that's what we want to show at least. Well, n plus 1, that's just going to be 1 over the square root of n plus 2, which is less than or equal to 1 over the square root of n plus 1, because 2 and 1 here, this again makes a bigger denominator, hence a smaller value. So that checks out. Okay, now we want to take a look at our limit. So again, the limit as n approaches infinity of b sub n, but we're going to plug this in as 1 over the square root of n plus 1. So 1 over the square root of n plus 1, that's going to be 1 over infinity, square root infinity. But that's just infinity, so that's just 0. 1 divided by infinity is in fact 0, so that checks out. So we know then that this converges. Okay, so we've shown that this converges. We can now estimate. So let's talk about estimating the sum. So a partial sum S sub n of any convergent series can be used as an approximation, as a reminder, to the total sum. So if we want to know the infinite sum, but we don't really know how to find it, we can always approximate it using a partial sum, and we can be more exact the further out we go. But it's not really all that useful unless we can also estimate the accuracy of the approximation. So the error involved with using our infinite series being approximately equal to our partial sum is the remainder, as we know, r sub n, which would be equal to the infinite sum minus the partial sum. So it's kind of the rest of it. So if we add the first 10 things, then 11, 12, 13, 14, all the way to infinity is kind of what's going on for the rest. Now, any series that satisfies the conditions, this is kind of nice, any series that satisfies the conditions of the alternating series test, the thing we just got done doing, has an error that is smaller than b sub n plus 1, which is the absolute value of our first neglected term. So that means that if we were to take the 10th partial sum, okay, then our error, r sub n, would be less than or equal to, the absolute value here, would be less than or equal to our b sub n plus 1, i.e., b sub 10 plus 1, which is b sub 11. So that's our 11th term. We're not taking the 11th sum. We'd say s sub 11 if we wanted. We're taking the 11th term, and we're just thinking, okay, well, this 11th term is our maximum error. Now, this might seem a little bit unbelievable at first, but I think it makes a lot of sense when you consider the fact that your first neglected term is going to be kind of your biggest value that we're having from then on out, because we know it's decreasing. So it's the biggest term, but also we're not like adding anything to that term, technically speaking, because if the first one's positive, let's go to the harmonic series, right? So if we have 1, 1/2, 1/3, 1/4, 1/5, and so on. Okay, now it's alternating. So let's say positive, negative, positive, negative, positive, negative, okay? And let's say that we approximated with the first four terms, the S sub 4, okay? Well then, this first neglected term, B sub 5 here, 1, 2, 3, 4, 5, yeah. B sub 5 here is our maximum error. And the reason why that is because if you think about this, 1/5, then we subtract 1/6. We take off some of it, but not all of it. Just a fair amount of it. So if we take a look at Desmos really quick. Okay, so if we have like 1/5 minus 1/6, right? Oops, not 16. Okay, we get 1/30th, which is a pretty small amount. Okay, but then we add on 1/7. So then it kind of goes back up. And again, let's compare that to 1/5, 0.2. So it kind of makes up that difference, but not enough. And then we subtract 1/8. And in this case, then again, it knocks off a bit. But then we add it, so 1/9, and it kind of brings it back. But notice, every time we do this, we're getting further and further away from this 0.2. And so again, this 1/5 kind of sets our maximum error, because every subsequent value after it will either be subtracting it to take it away from that, or adding back that subtraction, which would just kind of, but not entirely. So again, we're subtracting not all of it, but some of it, and then we're adding not all of the stuff we subtracted, but some of it, going back and forth. Okay, so basically, in this case, the fourth partial sum would be an approximation for the infinite sum with an error rate of 1/5. So that is essentially what we have. So we can take a look at, how good is this as an error? So like 1 minus 1/2 plus 1/3 minus 1/4 is 0.583333. So 0.58333, repeating here, with an error of no more than our 1/5, which is 0.2. Which in this case isn't particularly amazing, because if you think about it, if we're saying this is 0.58333 repeating, then we're saying plus or minus 0.2, so that is like, it could be up to like 0.78 or down to 0.38. So that's not amazing, but again, we only did the first four, so it would make sense we're not being that accurate. Okay, so let's take a look at this estimation theorem. This is officially where we define it by theory. Okay, if our infinite sum is an alternating series where b sub n here is greater than 0, again, so that is one of the requirements of our alternating series test, and it satisfies these two conditions: b sub n plus 1 is less than or equal to b sub n, and the limit as n approaches infinity of b sub n is 0. So again, if this passes the alternating series test, then r sub n, the absolute value of our remainder, is equal to the absolute value of our infinite sum minus our partial sum, which is less than or equal to our b sub n plus 1, our first neglected term. That's what we have here in our alternating series. So again, this is just saying, okay, well, if we have something that converges and meets these requirements, because it converges because it meets these requirements, then we can find our remainder by just taking a look at our first neglected term. And this is kind of nice because it means that we don't have to do some kind of integration, which is good because try integrating something that's alternating. Like we don't have methods for that, like, or at least we don't know a method for that yet. We don't know how to deal with this alternating. Because even though this is technically like a positive or a negative value, it's like a constant, like sometimes it's positive, sometimes it's negative. We can't just like pull it out as like a -1 when we're integrating. Okay, so that means that we'd be struggling to find the improper integral from like n to infinity or whatever. Okay, so instead we're going to go to this first neglected term as our error rate. Okay, so let's take a look at an example here. Test the series for convergence or divergence. If it is convergent, use the 10th partial sum to approximate the sum and determine the error. So let's first check, well, before we can check whether this thing converges or not, we're going to actually have to write it out. So instead of being given our sequence, we can just see it. So 2/3, 2/5, 2/7, 2/9, 2/11, and it's alternating minus, plus, minus, plus. Okay, so let's start with the alternating portion. That's -1 to something, to the n or n minus 1. So if we want it to be positive, our first term's positive, we would say n minus 1. Because again, 1 minus 1 is 0, positive. We could also have said n plus 1. That's fine too. So we have some sequence. And we're going to start at 1. Now, it's pretty normal to start at 1, but technically speaking, you're the one writing the sequence. You can start wherever you want. But in general, and in the homework, they usually just accept like n equals 1 so that it's kind of more consistent. And it's normal to start at 1, the natural numbers, but you'll sometimes see them starting at like 2 or 0 or whatever. Okay. So then we go to infinity. So that's our alternating portion of it. Now let's talk about our b sub n. Now let's take a look at this. 2, 2, 2, 2, 2. So basically what I'm thinking is I'm breaking this down into kind of parts. So I'm just working on the top right now. And on top, it's always 2. So we know it's 2. Now on the bottom, it's changing. But 3, 5, 7, 9, 11, we recognize that this is itself a sequence. 3, 5, 7, 9, 11. And if you recall, this thing here is an arithmetic sequence, something you might remember from pre-calc. That's a common difference of 2. Anything that has a common difference is arithmetic. And as a reminder, an arithmetic sequence is just a linear equation. So we have two options available to us. One, if you remember the sequence of an arithmetic sequence, so like a sub n, this is an arithmetic sequence, is equal to a sub 1, our first term, plus n minus 1 times d, our common difference. So for us, this is a sub n is equal to our first term, 3, plus n minus 1 times our common difference, 2. Which means we have 3 plus 2n minus 2, which is 2n plus 1. So if you remember that, cool. Now for me, whether I remember arithmetic sequence or not is kind of just dependent on if I've been doing it lately. And since I've been dealing with sequences lately, it's kind of on my mind. But a lot of times I don't really trust this formula. I don't really remember this one, and I don't expect you to necessarily remember something like that. But it's enough to recognize this as linear. This is linear. So if we think about it, and we can actually graph this and see it, that it's clearly linear. So our first term is 3. Our second term is 5. Our third term is 7. Our fourth term is 9. And so on and so forth. That's so clearly linear. Okay? Now, we just need to write an equation of a line that has this path. Now, if it's going up by 2 for each one, that tells us clearly our slope is 2. So as a reminder, mx plus b is a linear equation. So for us, our m is 2. So we have our a sub n is equal to 2x plus some b. Now we can do this real quickly. We want our first term, that is 2 times 1 must be 3 to have this first term be 3. So 2 times 1 is 2. Subtract the 2 over, 1 equals b. So 2x plus 1 would be a linear equation defining this pattern. So we have our 2n plus 1. Okay. So again, you don't need this because it's linear. You know how to write linear equations. Like you've been doing that since 7th grade probably. So there's really no need to think about it this way. And like I said, that's why I don't really remember this formula ever, pretty much. Okay, so this is our sequence. All right, we've written our sequence. And again, the idea here is that in general, when I'm trying to write my sequence, I break it down into smaller parts because when I'm looking at it as an entirety, it's really overwhelming for me. So like I started with the plus or minus portion. Then I looked at this top. Well, it's just 2. Okay, cool. Then I looked at the bottom. Well, it's following this sequence. And then I want to check it. So when n is 1, 1 minus 1 is positive. That's good. That checks out. 2 over 2 times 1 is going to be 2 plus 1 is 3. So 2/3 is our first term. So it's a positive 2/3. The next term, we'll just double check. It will go to a negative, so that's good. 2 over 4 plus 1 is 5. 2 over 5. Well, that's okay. So again, once we write it, you need to check it. Okay, it's working. This is good. Because sometimes you might think, oh, this looks good, and you write it, and then you realize, oh, no, that doesn't really work out. But that's okay because then we can, use what we know and make the changes we need. Okay, so now we need to see, does this thing converge? So as a reminder, we need to first see, okay, is b sub n plus 1 less than or equal to b sub n? So if we take a look at it, again, our b sub n here is 2 over 2n plus 1. So b sub n plus 1 would be 2 over 2 times n plus 1, which would be 2 over 2n plus 2 plus 1 is plus 3. Okay, so we're seeing is 2 over 2n plus 3 less than or equal to 2 over 2n plus 1. And again, I think it's pretty obvious. The tops are the same, so we're just looking at the bottoms here. The bottom here is a bigger number, always, so that does check out. Okay, so now we're going to take the limit as n approaches infinity of 2 over 2n plus 1, our b sub n. So at infinity, this would be 2 over infinity, which is 0. So that checks out. So this meets the requirements for our alternating series test. Because it meets those requirements, then we know that our remainder, r sub n, will be, the absolute value will be less than or equal to b sub n plus 1. So that's our error rate, but let's first find the sum then. So we want to find the 10th partial sum. So we're going to use this thing, but we're going to do it for 10. So n equals infinity to 10, or excuse me, n equals 1 to 10. So we're going to go over to Desmos for this. And if we go to keyboard, functions, calculus, oops, I went past it, sum 1 to 10 of negative 1 to the n minus 1 times 2 over 2n plus 1. Okay, and we get this value. 0.383842095297. Okay, now we need to find the error rate, but again, the error rate on our 10th partial sum will be less than or equal to b sub 11. So let's think about what is b sub 11. B sub 11 would mean that we're plugging in 11 into our b sub n portion, just this portion. So that is 2 over 2 times 11 plus 1. B sub n again is the portion that isn't the alternating portion of it. So it's this bit. So I don't have to worry about what sign it is. Okay, because again, b sub n is always positive. Because again, this portion is always positive. The rest of it is the alternating signs. So that is the absolute value of r sub 10 is going to be less than or equal to 2 over 23. Okay, now keep in mind when we have this absolute value, as a reminder, that's basically saying r sub 10 is less than or equal to 2/23 and it's greater than or equal to negative 2 over 23. So we have a plus or minus region because of this absolute value here. So if we take a look at that 2 over 23, that means our error is plus or minus this 0.086956. We often would just say that the error rate is 0.086956 217,391, but it's important to note that like this is our approximation, but we could error plus or minus that quantity, this portion here. So it's kind of a larger region of error than we've seen, but that's again easily fixable by just taking the sum out further. So like if we just did it out to say 100 terms, it'd be 0.42. Well, clearly then it's kind of going up, and then you would just have 2 over the 101 terms, so that would be 2 times 101 plus 1, and we get that, and we could see then that it's actually this positive side of it. Realistically speaking, it's only on the plus. But anyway, so that is our approximation. Okay, let's take a look at another one. Test the series for convergence. If it's convergent, 10th partial sum to approximate it. Okay, so let's first take a look at whether this thing is convergent. So again, this is our b sub n. So b sub n is n squared over n cubed plus 1. Okay, now this one is going to be maybe a little bit harder to show our b sub n plus 1. Because this is n plus 1 squared over n plus 1 cubed plus 1. Okay, so the problem here is that both the top and the bottom are kind of changing. And you might say, well, the top is growing, sure, but the bottom's growing faster because it's cubing instead of squaring. So that should hopefully maybe imply that b sub n plus 1 is less than or equal to b sub n, but that's not very definitive. And so what we're going to instead do is, I don't really trust that this is true. Okay, you know, you may hope that it's true, but hope isn't a good enough proof of that statement. And so instead, I'm just going to switch over to the derivative. So that is to say, if I think about this like b of x, essentially, that would be x squared over x cubed plus 1. And I'm going to take the derivative of it, b prime. And that would be 2x times, so it's the derivative of the top, it's quotient rule as a reminder, derivative of the top times the bottom, x cubed plus 1, minus the derivative of the bottom, 3x squared times the top, x squared, all over the bottom squared, x cubed plus 1 squared. Okay, so if we clean this up a little bit, we get 2x to the 4th plus 2x minus 3x to the 4th over x cubed plus 1 squared. So cleaning this up just a little bit more, we see that this is going to be 2x minus x to the 4th over x cubed plus 1 squared. Now we want to know, when is this derivative less than 0? Because that would mean it's decreasing. Okay, so now if you remember, when we're talking about like inequalities, inequalities are we basically have to think about critical values, and critical values are found at points of undefined, points when the function is undefined, and points when the function is 0, equal to 0. So let's think about undefined first of all. When is this undefined? When x is negative 1. Negative 1 plus 1 would be 0. But we only care about n's from 1 onwards, so that we don't really have to worry about. So instead, we're just going to look at the top. And basically, we're thinking, okay, well, when is this 2x minus x to the 4th going to be less than 0? Because again, that would make that 0. Now, again, just to point out is that technically speaking, we can't just keep track of this sign. We have to treat it like an equal sign. So 2x minus x to the 4th is equal to 0 because, again, we're looking at critical values. So the less than or equal to keeping track of it only works with linears, and this is clearly not linear. Now we can factor this, pull out this x. So 2 minus x cubed is equal to 0. Now, x equals 0 is one of those solutions. But again, just like in the previous one, x equals 0 isn't part of the domain we care about. So we're just going to focus on this one now. Okay, so solving for this, we move it over. We have 2 equals x cubed. So that means if we take the cube root, we end up with the cube root of 2 is equal to x. Okay, so basically what we have then is a critical value at cube root of 2. Now, this is greater than 1. Let's take a look at it really quick. The cube root of 2 is 1.25. Yeah, so it's greater than 1 and less than 2. Okay, now we know it's open at this point because at that point the slope would be 0. So then we're thinking, okay, well, when is this thing going to be negative? So we want to see when is this statement going to be true right here. So we'll take a look at when is this statement true. So let's take a look at 1. 2 times 1 minus 1 is less than 0. So 2 minus 1, that would be 1 is less than 0. That's not true. So we're not shading in that area. That's promising for us because we're hoping then that this will work. So 2 times 2 minus 2 to the 8th, or 2 to the 4th, is less than 0. So 4 minus 2 times 2 is 4, times 2 is 8, times 2 is 16. That is, in fact, less than 0. So we have a negative slope from the square root of the cube root of 2 onwards. Now, we are starting at 1. So technically it's actually increasing but then it drops down. And in fact, if we look at this thing, if we take a look back at our function, x squared over x cubed minus plus 1, this thing, okay, we can see that this statement here, this is where it has a slope of 0. This is the square root of, or the cube root of 2. Technically at 1 we're at 0.5, so 1/2, and at 2 we're down. So even by our standards, even though it's increasing a little bit, by our calculations, 1, then 2, then 3, then 4, it still is decreasing the whole time. But that's not really all that important. What's really important is that we are decreasing at some point until infinity. And that's sufficient to show that this would, in fact, meet the requirement we need of b sub n plus 1 is less than or equal b sub n. So, check. So this one's a little bit more challenging just to make sure that this is working. Okay, so we checked the first one. Now, the limit as n approaches infinity of n squared over n cubed plus 1. Now, if we look at this, you're like, oh, well, that's infinity over infinity. Well, infinity over infinity is indeterminate. Technically, infinity over infinity is indeterminate form infinity over infinity, and you could, if you needed to, use Hopital's rule. Personally, I wouldn't in this case because that's overkill. I'm going to use pre-calculus concepts, our algebra. So at the infinites, we can think about this either as divide everything by the highest power to n, or I just think, what's the biggest power on top? N squared. So the limit as n approaches infinity of this is the same as n squared over the highest power here, n cubed, which is the same as 1 over n. So the limit as n approaches infinity of 1 over n is 0. So that's check. It converges. So we've shown the two things are true, so it converges. Now let's approximate this sum. So I'm just going to take it to another page now, since that one was getting long. Okay, so we know it converges. Now we're going to use the 10th partial sum. So s sub 10 is equal to, and that was foolish of me, let's just put it way over here, the sum n equals 1 to 10 of negative 1 to the n plus 1 n squared over n cubed plus 1. And we'll go ahead and see what that is. I should really stop erasing the sum that I'm doing so I don't have to keep going to this, but whatever. Sum is n equals 1 to 10 of our -1 to the n plus 1. Notice it's an n plus 1 this time. Times our n squared over n cubed plus 1. Okay, so we get this value here. So 0.1920886911123. Okay, now we need to find the error rate. And again, the error rate, our remainder, is less than or equal to b sub 11 here. So we're just going to plug in 11 into this thing. So 11 squared over 11 cubed plus 1. Okay, so our rate here is less than or equal to 0.0908408408408. That's repeating, obviously, so it's a fraction of 121 over 1332, but that's our error rate. Okay, cool. So now let's go ahead and talk about absolute and conditional convergence. So what we've just talked about is our convergence of our alternating series. But when we talk about absolute convergence, this is actually a stronger statement than what we call conditional convergence. Basically, if something converges using our alternating series test, then we know it converges conditionally. But if we could also show that it converges absolutely, then it's actually a pretty strong statement that helps us in other things in more advanced math topics. So one of the weird things about conditional convergence is that it kind of breaks rules that we would expect. So if we think about like a series, right? A series is a bunch of adding and subtracting. And technically speaking, we know that if we're adding numbers together, the order doesn't matter. But if we take a conditionally convergent series and change the order, it does change our sum, which is weird. But an absolute one doesn't change. It works exactly as we'd expect. So that's just one aspect of an absolute convergence that's going to be kind of handy for us. So anyway, a series, and here's another thing, is if we can just show that the absolute converges, then the rest of it will converge too, because absolute convergence is a stronger statement. So we, in a practical sense for us, we use absolute convergence just to show that some series converges. So a series, a sub n, is absolutely convergent if the series of absolute values is convergent. So basically, if we just ignore the signs and just treat them all as positive, if that converges, then our series is absolutely convergent. It converges. So this is useful for our alternating series for sure, but also for series that might change from positive to negative. But not in some kind of alternating fashion. So maybe it's positive, positive, then a few negatives, and then a couple other positives, and so on and so forth. Like, there's no alternating positive, negative, and so we can't use our alternating series test. So instead, we have to treat them all as positive and see, hey, is the absolute convergent? Okay. In general, what we want to do is we want to use this absolute convergence to turn our series into just something we know converges or not, like a p-series or a geometric series. If we can show that, cool. Now, obviously, this wouldn't work on our harmonic series, our alternating harmonic series, because the alternating harmonic series, if we just absolute value, would just be the harmonic series, and we know the harmonic series doesn't converge, so that wouldn't really help us. But in general, we want to use it to convert it into something that we know converges. Okay. So, a series is called conditionally convergent if it is a convergent series, but not absolutely convergent. So our series converges, but our absolute value diverges. It's called conditionally convergent. And again, it's a weaker statement than absolute convergence. So if a series is absolutely convergent, then it converges. So if we can show absolute convergence, then we know the series converges, period. And that makes sense logically, because if you think about it, you know, if some series that we're just adding up the whole thing converges to a number, because we're just adding infinitely many things and it converges, then clearly if we're subtracting some of those things, it would also converge. So again, if we can show this absolute convergence, then that's great. But there are plenty of series that are not absolute convergent, that converge, and we call them conditionally convergent. But again, if we can show absolute convergence, then that's great. That would be super awesome. So let's take a look at it. Determine whether the series converges or diverges. Okay, that's a typo. That should be n. It's really close on the keyboard, okay? All right, so we have our sum, n equals 1 to infinity. All right, of cosine n over n squared. Now, cosine n over n squared, if we think about this, cosine goes between -1 and +1 depending on n. So if we take a look at this thing, we can go, I'm not going to delete that one. Oh, I guess I don't really need it anymore, but whatever, over x squared. Okay. So if you notice, some of the time it's positive, some of the time it's negative, some of the times it's positive, and so on and so forth. And you know, it's not always positive, it's not always negative. So we can't use alternating series because it's not changing all the time. And so what we need to do is hopefully find that like absolute convergence would work. So what we're going to do is we're going to think about this n equals 1 to infinity of the absolute value of cosine n over n squared. Now, if you think about this, first of all, cosine n is between 1 and -1. So the absolute value of this thing would mean that we're now going between, so the absolute value of cosine n is between 1 and 0. And n squared is always positive anyway, so it's not really all that important. This is like saying the sum of absolute value cosine n over n squared. Okay, so basically cosine n is somewhere between 0 and 1. So if we think about this thing, that means that cosine n absolute value over n squared is less than or equal to 1 over n squared for all n, because again, the bottom's the same. This would go between 1 and 0. So it's at most it's 1, and at least it's 0. So usually it's less than 1, but sometimes it's equal to it. So by direct comparison, this is less than or equal to this one, and we know that this converges. So since this converges by direct comparison, and this is less than or equal to, then this must also converge. So we know then that this converges. Again, because this absolute value converges. So we would say that this series converges absolutely. So then that is a very strong statement. So it converges, period. Okay. Let's take a look at another one. Determine whether this converges absolutely or not. Okay. So we're going to do the same basic concept here. Is we're going to go, all right, well, we're going to take the absolute value of this. So that would just make this positive 1. So that is to say 1 over n squared plus 1. Okay? This is the sum that we're dealing with now. Now, again, same thing. We know that 1 over n squared plus 1 is less than or equal to 1 over n squared, which again, this converges by the p-series. So this converges. And so this converges absolutely. It's nice and simple. So again, if we turn it into an absolute value, then we can go back to our old methods of either the integral test or direct comparison. Um, so anyway, now again, I want to just talk about rearrangements real briefly as a reminder of what I had said earlier. Basically, the question of whether a given convergent series is absolutely convergent or conditionally convergent has bearing on the question on whether or not the infinite sums behave like finite sums. And that's why absolute convergence is so important in a more theoretical concept in more advanced maths. Okay? Not like theoretical as far as it's all just make believe or whatever, but just in more advanced math. In more advanced math, we tend to do a lot of theoretical stuff. So anyway, rather than like actual computations. But anyway, so if we rearrange the orders of the terms of a finite sum, obviously the value of the sum is unchanged. So, if we had something like 1/2 plus 1/3 plus 1/4, well, clearly 1/4 plus 1/2 plus 1/3 should be the same because we know our math rules. However, that's not always the case with infinite series. If we have an absolute convergent series with some s, then any arrangement of it will have the same sum. However, any conditionally convergent series can be rearranged to be given a different sum. So an infinite sum could be different if it's not absolutely convergent. So the order would matter. And again, why is this important? Basically, one of the methods of proving what a infinite sum of a series is through rearrangements. So basically, they do a bit of clever thinking and rearrange them so that like groups of values will cancel out, so that you can then like simplify it down to be some specific number rather than approximation. And so if you can show it's absolutely convergent, then you can rearrange and get something. But if it's not absolutely convergent, then you can't use a rearrangement to show what a series would add towards, because we know that rearranging it would cause differences in the sum. So that's why it's important in a more advanced math concept, is when we're not doing approximations, we're actually finding exact values of our infinite series. And doing that requires clever thought, and one of the clever thoughts is rearrangements and trying to look for patterns in that rearrangement, but you can't rearrange it if it's not absolutely convergent. So that's important in that situation. Anyway, but like I said, for us, in a practical sense, if we can just rewrite it as an absolute and show that that converges, then we'll do that because that's usually easier. So, anyway, that is our alternating series and absolute convergence. Thanks for watching.